Dear students, we will now dive deeper into log data analysis, beginning with a comparison between the state of the art and the state of the practice. Here is an example log from Android stability testing. The full log contains 65,000 lines, and what you see here is just a small excerpt. This slide illustrates the process of creating execution logs from the code perspective. Typically, a logging library is employed to capture and manage logs effectively. In Python, the logging module serves as the standard tool for setting up logging functionality. The example provided demonstrates the configuration of a logger. The process begins by creating a logger specific to the current module and setting its minimum logging level to debug, ensuring that all log levels are captured. Next, a handler is added to direct the logs to the console with a defined format that includes timestamps, module names, log levels, and messages. Finally, the example showcases the use of different log levels: debug, info, warning, error, and critical to categorize log messages based on their importance or severity. Here we outline the primary objectives of software log analysis. One key goal is to determine with a straightforward yes/no answer whether the system's internal state indicates abnormal conditions. Another objective is to identify the nature of the anomaly, whether it is a performance issue, security breach, or functional failure. In distributed or microservice-based systems, log analysis seeks to identify the root cause by pinpointing the specific service or component responsible. Additionally, the analysis may focus on highlighting the most suspicious events within the logs, offering software engineers clues about where to investigate the root cause of the failure. Now we turn our attention to the state of the practice. The information presented is sourced from a study conducted with ASML and 4 other companies based in the Netherlands. Standard industry practice for identifying suspect events in log files typically involves leveraging domain knowledge combined with filtering or search techniques. Domain knowledge allows engineers to make informed guesses about what to search for in log files. It guides them towards specific keywords or error codes to efficiently filter or grep through extensive datasets. However, this approach has a notable drawback. It heavily depends on individual expertise, making the process less repeatable and challenging for someone who lacks the same level of domain knowledge. This reliance can hinder scalability and consistency in log analysis across different team members or organizations. This example illustrates a query-based approach to log analysis using grep to search for specific patterns in a log file. In this case, the query UIDaemon screencaster stop helps quickly identify relevant log lines where this exact phrase appears. If you have a good idea of what might be wrong, using a specific query like grep UIDaemon screencaster stop can quickly pinpoint relevant log lines. However, in the absence of a clear hypothesis, this approach can feel like searching for a needle in a haystack, especially when dealing with thousands or millions of log entries. This brings us to the first state of the practice approach for log analysis, which we can refer to as the one-file approach. This method involves manually reading the logs or leveraging domain knowledge to identify keywords, which are then used to search through the log files. Another common industry practice for log analysis is the two-log file approach. In this method, a log file from a successful or good run is compared to one from a failing or suspect scenario. The goal is to identify anomalies or discrepancies between the logs that may point to the root cause of the failure. This comparison can be performed manually By visually scanning both logs for differences or automated using tools like diff, kdiff3, or beyond compare, which highlight discrepancies. This approach helps software engineers focus on deviations that might be responsible for the issue. To use this technique successfully, it is important to mask out consistently varying parts of the logs, such as timestamps, to avoid irrelevant noise in the comparison. So, we now have two approaches: the previously mentioned one-file approach and the two-file approach. The two-file approach can be considered better in the sense that it is less dependent on individual expertise. However, better in this sense does not imply that it is faster or more effective at locating anomalies. Now we shift focus towards state-of-the-art research in log analysis, where deep learning dominates the landscape. The reference survey highlights the breadth of research in this domain, analyzing methodologies for anomaly detection across diverse use cases. A reasonable software engineer wouldn't jump straight into deep learning but would start with simpler solutions instead. And there are three main reasons for this. First, deep learning is expensive and complicated to train. Training models for log analysis takes a lot of resources, both in terms of computational power and expertise. It's not practical or efficient in many cases. Second, logs are generated in massive volumes, and running deep learning inference on all of them can be costly. Third, transfer learning or foundational models may not be practical for log analysis. Unlike in natural language processing, NLP, where models can be pre-trained on massive datasets and then fine-tuned for specific tasks, logs lack similar infrastructure. Open datasets for logs are limited and logs are system-specific, meaning techniques effective in one context may not generalize well to another. This slide highlights the apparent gap between academic research and industry practices in log analysis. On one side, we see the state of the practice, representing pragmatic, low-complexity approaches like using text editors, grep, or diff tools. These methods rely on domain knowledge and are quick to implement but may struggle with scalability and deeper insights. On the other side, the state-of-the-art showcases advanced deep learning-based techniques. These methods, while powerful, involve significant complexity in terms of parameter tuning, long training times, and often require labeled datasets, which may not be readily available in industrial settings. This gap underscores the challenge of transitioning academic advancements into practical, industry-ready solutions. In the next video, we will explore techniques and strategies that aim to bridge this gap, combining the best of both worlds to enhance log analysis capabilities,